Alright, so in this video we're going to be talking about polarity. So we're going to discuss what is a polar molecule and also how do you determine if a molecule is going to be polar or nonpolar. So the first thing you are going to look at is the difference in electronegativity. So electronegativity, remember, that is the ability of an atom to pull electrons towards itself in a bond. So how attracted are the electrons to that nucleus? Is it able to pull the electrons more towards its side? So when there is a difference in electronegativity, that creates a dipole. So it creates a slightly negative end and a slightly positive end. So most bonds, most covalent bonds are going to be considered to be polar, except for a few. So when an atom bonds to itself, like H and H, or nitrogen bonding with nitrogen, or F with F. Okay, obviously there will be no difference in electronegativity here. That is definitely going to be a non-polar bond. Now, there's another one that is going to be considered nonpolar, and we see that a lot with organic compounds. It's C and H bonding together. Those are going to, that right there is going to be a nonpolar bond because the difference isn't great enough to create that dipole. Now, the higher the difference, the more polar the bond becomes. So that means that the atom is able to attract the electrons more towards itself, and it does create a higher electron density around that atom. All right. So once we get to a certain point, like after 1.8, that bond is usually going to be considered to be ionic because the electrons are actually pulled off the atom. Now, the more electronegative atom will have the negative end because it attracts and pulls the electrons there, and then the other atom will have the positive end. So when we look at a molecule, in order for a molecule to be polar, it has to have two things. It has to have polar bonds, which means that you have atoms that have an electronegativity difference great enough to be considered polar, to pull the electrons. And also an asymmetrical shape. So when you have those electrons being pulled to one side, do you have an equal pulling on the other side of the molecule? That will end up canceling out the polarity. So in order to be considered asymmetrical, the dipoles do not cancel out. Okay? The easiest thing to do if you're trying to determine if something is asymmetrical is you look at the central atom. Okay, if the atoms on the outside match and you have a symmetrical shape, then it's going to be nonpolar. If they don't match, automatically the dipoles will not cancel. So this molecule right here, because I've got H, H, Cl, and Cl, I automatically know the dipoles will not end up canceling, so that is not going to be symmetrical. Also, the shapes, when we're looking at the shapes, a lot of the shapes with lone pairs on the central atom create asymmetry because remember, those lone pairs repel strongly, so they push the atoms closer together than they normally would be. So typically the shapes that have lone pairs on the central atom are going to be considered to be polar or asymmetrical. So those shapes, either of the bents, trigonal pyramidal, there's seesaw, T-shaped, square, pyramidal. Those are going to be considered to be polar or asymmetrical shapes. Usually we look at the shape more than anything because, like I said, most bonds are going to be considered to be polar. Usually there is a difference great enough for that. All right, so let's look at some examples. We're going to do this one last. This is an organic compound. You would never be asked to draw this on the AP test. So let's look at CH3F first. Okay, so we have to look at, you have to draw the Lewis structure. I mean, after a little bit you may not have to, but you really want to check for lone pairs. Okay, so when we draw this out, this is what we're going to get. Well, automatically I do know I have some polar bonds. The CF bond is going to be polar. Well, is it symmetrical or not symmetrical? Well, H, H, and F. So we have 1, 2, 3, 4. That's a tetrahedral shape, which is considered to be symmetrical. However, this is different than all of the others. So that is going to be considered a polar shape or asymmetrical. So is it polar? Yes. Now, it's important to note, I could have an F here too. That would still be considered asymmetrical because this is a two-dimensional drawing. When you actually build this structure, you can see that they do not cancel. The dipoles are not going to cancel for that. So if the atoms match, that is symmetry. If the atoms do not match, automatically it's asymmetrical. All right, let's do CH4. Well, nope, there are no polar bonds here. It's 1, 2, 3. It's tetrahedral, so that means that it's symmetrical. So there's no polar shape. It's nonpolar. Now CCl4. This is what I'm going to get for my Lewis structure. Well, then I can put the lone pairs there. All right, so, well, does it have polar bonds? Yes, C and Cl, that would be polar. 1, 2, 3, 4, that's a tetrahedral, so technically it's symmetrical. Are all the atoms the same? Yes. So even though it has polar bonds, all of them end up canceling. It is non-polar. All right, let's look at NH3. All right, so this is why it's important to actually draw the Lewis structures out. If I look, nitrogen has 5 electrons available for bonding. Hydrogen has 1, so there's 8 total electrons. It's only 2, 4, 6 right now. Here's the last 2. Okay, so now that is my Lewis structure. Well, polar bonds, yes. Polar shape, well, we've got a lone pair and 3 bonding pairs, so that's going to be trigonal pyramidal. That is an asymmetrical shape. So is it a polar shape? Yes, it's asymmetrical. Is it polar? Yes. That's why you have to draw these Lewis structures, especially when you have a structure like this. Okay, so 2-pentanone. Okay, so again, you would not be asked to draw this. All right, so this is my structure for 2-pentanone. So let's check for polar bonds. We've got CH, but we've got a CO bond here, so yes, we do have a polar bond. Polar shape. Well, the shape here is a little undefined. It's going to end up being a zigzag for a lot of this, but really what you need to hone in on here is you've got the CO bond. There's nothing here to cancel that out. That is the only CO bond that I have right there. That is definitely creating some asymmetry in the molecule. So is it a polar shape? Yes. Is it polar? Yes. Is it very polar? No, it's only slightly polar. But you can definitely say this is polar. Let me show you another structure. I have this. So basically the same molecule here, but I've just moved the CO. I just want to point this out because again, this, if I look at this, it looks symmetrical. Look, I've got 2 carbons here, 2 carbons here. It looks like I could cut it down the middle and it could be symmetrical. But you have to remember when you're looking at these Lewis structures drawn out like this is not how the molecule will actually appear. So if we were to build this molecule, we would see that it is asymmetrical. So again, this molecule would still be asymmetrical and be polar.